Hey everybody, nice to see you. A little while ago, I put up a short about power usage in the museum, and a lot of folks watched that. So it occurred to me that maybe we could talk about power for a while and just how all this stuff gets its power, and what factors lead to higher or lower power consumption for all this old hardware. Before we go through how the power system works, it's important to mention that everything that we have here in the museum is sort of a minimum viable configuration. Due to space constraints, they couldn't bring an entire power room in here. Nevertheless, we have a representative sample of all of the major parts of a power system. So we should be able to go through everything that you need to know in order to become an apprentice power man in a 20th century central office. Okay, so let's get into it. Almost all of this equipment runs on DC power. It's kind of easier to point out things that aren't using DC, which includes the lighting, HVAC, some of the electric motors, one of the ringing machines, and of course, the rectifiers that actually convert AC to DC. Everything else, including the switches themselves, runs on DC. In particular, they run from batteries down in the basement. A big reason for this was because the carbon transmitters, or microphones, in almost all telephones, even up until the 1980s, required a constant source of DC power to work. Originally, this was provided by batteries in the telephones themselves, but soon enough, the telephone companies figured out that they could just put big batteries in the central office building instead of small batteries in each and every telephone. And it wasn't just the telephones that needed power. Even before dial telephones were a thing, the operator's switchboards had relays inside. DC relays are a lot easier to make, especially when you need to make millions of them. And finally, well, 60 hertz AC power simply wasn't available when the telephone companies started doing their thing. Many people don't realize this, but telephone service actually predated consumer electricity in many areas. So the entire telephone plant was built to rely on these DC batteries. And in the first decade of the 1900s, telcos were putting big strings of lead-acid batteries in their central offices and using them to supply the entire subscriber base, not to mention the switchboards and other exchange logic. This has the pleasant extra benefit that if the power went out, your telephone would still work, since it wasn't dependent on mains power to function. Batteries also provide a source of relatively quiet power for the subscriber's talking path. After all, the telephone would be pretty much useless if you had to deal with AC noise on the lines all the time. In fact, the telephone companies were so concerned with providing a quiet talking circuit that special filters were installed that separated out the signal battery, which was used to operate relays and other mechanical apparatus, from the talking battery, which was actually sent out to the phones. If we plug a phone into the noisy signal battery, we can hear this sound created by the switching machines as they operate. You actually could hear some of these noises during the call setup process while your telephone is connected to the signaling logic. But once the talk path was established through to the called party, those large inductor capacitor networks were cut in, and most of the noise was hopefully eliminated. But all of that requires a charging system to keep all these batteries topped up. That was the job of motor generators like this one here. In the CO, we get commercial three-phase AC from the power company. That feeds directly into these generators. Nowadays, of course, there's solid-state rectifiers, but back then, the easiest way to convert lots of AC to lots of DC was to have a bunch of these in your power room. This generator and others like it were cut into the charging circuit on demand and would keep the batteries floating at a nominal 48-volt potential. Battery floating is a method where the batteries are kept at a steady voltage regardless of the amount of demand placed upon them. As the load goes up, more generators are started and cut in, and when the load dies down, generators are shut off. Here's a fun side note. If you were building your telephone company in a town that didn't have utility power yet, Western Electric was happy to sell you water-powered generators. This large box here is the starter for this generator. Starters like this were necessary because three-phase AC motors can produce 100% of their torque output at the moment that power is applied. Since there's so much mass to spin up here, it's quite possible that the connecting shaft or coupling would break in half the instant you turn on the motor. Inside the starter, 208-volt three-phase AC feeds into a set of auto transformers, which are cut in and out by the starting lever on the right. When the starting lever is pushed forward, power is sent through the auto transformers, allowing the motor generator to start gently. Once it's up to speed, you can quickly pull the lever back to connect the AC directly to the motor for running on full power. The starter lever was locked in position by this solenoid here. If there was an overvoltage or high temperature condition in the AC circuit, the solenoid released and shut down the motor. On this end of the set, we have our DC generator, coupled to the motor by the shaft I mentioned earlier. This particular generator can put out 500 amps at 65 volts, or 32,500 watts, which is quite a bit more than your average laptop charger. When the power draw exceeds what one generator can deliver, additional generators would be cut in to take up the load. There were always enough generators to cover the maximum load on the office, plus one or two extra for backup. This one actually works, and our volunteer Jay got it spinning a while ago.
Okay, so this is the newest thing we have just got working. This is a motor generator set that would originally have been used to charge the lead-acid batteries that we use for powering all of our telephone switches here. It consists of an AC generator, AC motor, and a DC generator right here to generate 48 volts for charging the batteries. Right now we have this running in reverse. So we have 48 volts applied to the field and applied to the brushes, and we're basically spinning this as a motor right now. And pretty sure it's at full speed right now, and it's kind of scary to be around.
The motor generator sets are connected to the batteries through large circuit breakers. This one was made by ITE, and it's from the 1910s. It's so completely beautiful that I'm surprised that more of these weren't saved. Ours came out of the East CO in Seattle and was rescued by one of our founding volunteers before it was thrown in the dumpster. It wasn't always on this power board. We moved it here last year to make room for our new ringing machine and to put it somewhere where visitors could actually see it. This breaker features 3 make contacts. When the breaker is closed by this lever here, the top carbon contacts close first. These are sacrificial and can be easily swapped out just by unbolting them and putting on new ones. The second set of contacts are these right here. You can see the scarring and pitting from them opening and closing a bunch of times throughout their life. And finally, there's these laminated contacts at the bottom that make the connection last. These are what actually carry the significant portion of the current from the charging generators to the batteries. This breaker, and the smaller one down there, are designed to protect the batteries against overcharging and loss of generator power. Let's talk about overcharging first. If lead-acid batteries are overcharged, at least 2 really bad things can happen. First, they tend to off-gas. This might not be such a big deal, except that this gas is mostly hydrogen, which is totally explosive. The second problem is that the batteries could get overcharged enough to overcome the charging current from the generator and produce back EMF. Back EMF is voltage pushing in the reverse direction from the batteries into the generator. There's always a little bit of this back EMF inherent in the system, but when it becomes excessive, it's a problem. One of the main issues is that we could start turning the generator like a motor and try to send power upstream to the power company, which is a huge no-no. In the circuit breaker, these coils here react to back EMF, and when it reaches a certain tripping point, the armature will open the breaker and open the charging circuit. This circuit breaker also provides protection against loss of power. If the main AC feed is lost, the motor generators would shut off. And when the AC power is eventually restored, we don't want to suddenly start all of the generators at once. That would put a heavy instantaneous load on the power service. And if this were, for example, a factory and the power went out, you wouldn't want power being delivered to all of the machinery in a sudden, uncontrollable way. The coolest thing about this breaker is that it's automatic and can be controlled remotely. We installed some Allen Bradley controls here, and I can push this red button to close the breaker. I can simulate a back EMF condition by manually operating this guy here. Now the breaker is open, but no matter how many times I push the red button, it won't operate again until I manually close it. Now that I've done that, I can use this button to open the circuit remotely and then close it again with the red button. Besides being constantly charged, the string of batteries that supplies the main 48-volt power usually has additional cells that can be cut into the charging circuit during emergencies. These cells are usually 2 volts each and are known as N cells. The large motorized switch in the center of the power board can be set to no N cells, 1 emergency group, or both emergency groups. It's normally operated automatically, but we can operate it here with these buttons as well. There's also a hand crank to manually switch in the N cells if the motor stops working. However, there's a stern warning here to never use the hand crank without first removing the motor fuses. The switch has an auto-censoring device that will detect if it's moved off normal, and the motor will kick in and the crank will smack you in the face. No good. To the right of the emergency cell switch is this huge knife switch. This cuts in the charging generators to the first bank or both banks of emergency cells. It's really hard to move, even being fully lubricated. Another way to make DC to charge the batteries was the much beloved mercury arc rectifier. There are plenty of videos on YouTube that cover how these work. This one is just for a small office and only has a 50 amp capacity. It was used in remote offices that were normally unstaffed. Jay also got this one working last year, and it was really cool to watch it working. She needed ballast for the circuit, so she used a bunch of lamps in series, plus a little waffle maker that she picked up at Goodwill. Here's a clip for your enjoyment. Cool.
Let me post the video.
In real life, this whole charging system would be automatic. A relay like this one is arranged to operate in one direction when the battery voltage gets too high, and in the other direction when it gets too low. When either of these conditions occur, the power plant is reconfigured automatically to bring the voltage back into an acceptable range. Low voltage can be just as bad as high voltage, but for different reasons. When office load goes up and the charging capacity is insufficient to handle it, the voltage of the batteries in the string starts to drop. A 48-volt battery can go down to about 46 volts before things get serious. Once they discharge past a certain point, there's almost no saving them, and you just need new batteries. This would be catastrophic for a busy telephone office, so there's a lot of attention paid to keeping the batteries healthy and fully charged at all times. An older museum volunteer named John once told me a story about this. Back in 1963, he was working in the Parkway office, which is where our panel switch and this power board were originally installed. He and the other switchmen were hanging around at the trouble desk, and the radio was on. All of a sudden, a newscaster interrupted the regular programming and announced that the president had been shot in Dallas and was being rushed to the hospital. They all wanted to stay and listen to the radio, but they instinctively knew what was about to happen. John rushed down to the power room and manually fired up all of the reserve generators and checked the voltage level on the batteries. By the time he came back upstairs to the switch room, the huge influx of calls had already begun. The panel selectors were moving up and down over the frames like crazy, and the decoders were running at full blast. Soon enough, the groaning sound of the sender selectors became louder and louder. The panel switch didn't have enough senders to handle this huge influx of dial tone requests, and the rotary selectors were hunting endlessly to try and find any available senders to handle the huge incoming load. Alas, there was just no way that the machine could handle thousands of subscribers picking up their phone all at once. Upstairs in the number 1 crossbar exchange, the markers were firing as fast as they could, and the all markers busy alarms were continuous. I asked John what he and the other workers did to try to stem the tide, and he told me that there was nothing they could do. The machines did the best they could to handle this once-in-a-lifetime load, but many customers just couldn't get dial tone until the huge influx died down a few hours later. But thankfully, the generators and batteries held up, and there was no shortage of electric power, just shortage of computational power. So how much juice did all these machines actually use? Well, we have records of the daily power usage from the Parkway office in Seattle from 1959. And here we can see the power readings were taken twice a day, once during busy hour and once overnight when the load was its lowest around 3 a.m. We can see that the discharge load on the 48-volt battery string at 10:30 a.m. was between 1250 and 1300 amps. And at 3 a.m., it was a paltry 240-ish amps. Now, Parkway was not an incredibly large central office, and compared to offices in larger cities, it was downright cute. So you can imagine how this would scale for a CO with 3 or 4 or even more times the call volume. In common control systems like panel, and especially crossbar, the biggest contributor to power usage is concurrency. These machines don't take too much power to idle, but each relay in a control circuit, like a marker, consumes a certain number of milliamps. Since each marker does several operations in parallel, there are hundreds of relays operated all at once, or very closely together. And this adds up. So why doesn't the museum draw that much power? In the YouTube short I posted a while back, we found that we were drawing only 150 amps at peak load, which is far less than the numbers we saw in those tables. Well, again, it's all about concurrency. See, in the museum, we mostly only have one of everything, and each marker in our crossbar systems can only work in one set of link frames at a time. So even in our 5XB, where we have 3 markers, we only have one set of crossbar link frames, and only one marker can be accessing a particular set of frames at once. So the other markers will have to wait until the currently active marker has finished.
Right. So this is just a look at the unfiltered battery voltage in the museum, AC coupled, so we've taken out the 48 volt baseline, and you can see that there is kind of this constant noise, which is just about 1 volt, which is just what the museum does. It's a combination of what's going on here on our part of the museum and what's going on in the Lumen part of it, because they're using power from that same source as well. And then you can see these individual little spikes here where the voltage briefly goes up and down as a result of the marker in the number 5 crossbar activating, or the number 1 crossbar, or whatever. So in terms of the average baseline power use in the museum, you can think of it as this thick line here in the middle. And if this equipment was really running at absolute full tilt, you would see those spikes happening almost continuously, and then we would be using a whole lot more average power. But because even with our call simulator running, we're putting through, you know, what, Sarah, 5 or 10 calls?
So right now there's 15 lines and a maximum of 7 concurrent calls.
Yeah, so a few calls a minute is what's going through, you know, on the order of dozens at most.
Yeah.
Right? And that's way less than the full-sized machine, fully configured machine could do.
Regardless of the number of calls we have going through, one of the most substantial limiting factors is the size of our switches, and in particular, the number of link frames that we have. And let me tell you why that's important. So in our number 5 crossbar, we have 1 line link frame here. This is 1 frame. And then down there, we have 1 trunk link frame that looks very similar, right? And as a rule of these common control systems, 1 marker can only be working in 1 set of frames at a time. So even if we had 10 markers, we have 3, but even in the number 5, but even if we had 10 markers, it wouldn't matter, because if a marker seizes this frame and the trunk link frame, it'll always do both at the same time. That effectively locks out the switch fabric for the remaining markers. Now it's only locked out for like a fraction of a second, but that has the effect of queuing the marker operations where they all have to share this topology, this network. And in order to have any sort of real concurrency, we would have to have like 3 more of these things copy pasted so that the markers actually had opportunities to interact at the same time.
Right. And to give you a sense of scale, so our 1 subscriber line frame here, that has a maximum of 300 subscriber lines connected to it. When this was over on Mercer Island and it was the Adams office, it had, I don't know, maybe 6,000 or so subscriber lines. Like probably about
6 to 8 probably.
Yeah, exactly. And so it would have had 10 to 20 times as many subscriber lines, which means 10 to 20 times as many of these frames. So now when you have 3 markers, there's a much greater probability that they'll be able to work simultaneously because you've got many more subscriber link frames. And well, trunk link frames, they wouldn't have had that many more of, right?
You generally have half the number of trunk links as you do line links. So if you're a 20 line link office, that means you have 10 trunk links.
Right.
And there is some flexibility in that rule, but that was the basic design engineering rule for how to design these networks.
Right. So then the multiple markers would have had a much higher chance of being able to run simultaneously because they had different line link and trunk link frames to talk to.
Yep. Another question we get asked all the time is, why does the telephone system use negative 48 volts instead of positive voltage like everything else? Well, the answer has to do with electrolysis and corrosion. The original copper telephone plant extended to almost every home and business in the entire country, and all of that outside plant was susceptible to damage caused by electrolysis. Now, this chemical process is useful under some circumstances, but when it happens in the telephone plant, it slowly eats away at the copper wires. And over time, that can add up to damage that would cost a lot of time and money to repair. Way back in the mists of history, some really smart person figured out that if you connect the positive end of the battery to earth ground and use the negative terminal as your voltage source, then electrolysis goes the other direction and the wires don't corrode. I promise you that after working with negative voltage every day, it just becomes the standard. I have the particular brain worms where negative voltage is normal to me, and positive voltage that's used basically in all other electrical circuits seems weird. So I guess it's just a matter of perspective. But let's get back to our power system. We're now moving from the charging circuit into the discharge circuit, which includes, well, everything that discharges the batteries. So the current is carried from the batteries to the load. But how does it get there? Usually, it leaves the batteries using large bus bars like this and goes into a power board like this one. This is technically called a BDFB, or Battery Distributing Fuse Board, and its main job is to provide paths from the batteries to the circuits in the office that need power. Now, this board has been modified somewhat over the course of its life, and even during its time here in the museum. Starting on the left side, we have these two large knife switches. These were originally part of a much larger set that distributed power to the main areas of the building. The amount of area served would be based on the amount of current it required, but you can generally imagine these to be a few aisles of equipment for each switch. Here, this knife switch is unused, and this one is the main power for the entire museum. Normally, these switches would not be used as on-off switches, but instead as emergency throwover switches for when fuses operate. If this 600 amp fuse blows for some reason, the frames depending on it need to be brought back into service as soon as possible. So the switch is thrown to the opposite pole, which it then uses a backup fuse. At this point, the original blown fuse can be replaced and the circuit thrown back to its normal position. In our museum knife switch, we've just removed the second fuse, so this functions as a regular on-off switch for everything up here. Next, we have a bunch of smaller distributing fuses to the other areas of the museum that need them. These fuses are switched by the main knife, so anything connected through here will be powered off when the museum is shut down. This includes some of the other accessories on this power board, the ringing plant, the DC to DC converters for our 24 and 130 volt service, and the big ringing machine over there. Each circuit in the museum is protected by a string of progressively smaller fuses. I'm going to show you a huge one right now. Just hang on. This guy here is a whopping 4,800 amps. They are placed in the charge and discharge circuits, and if they ever blow, you are in trouble. Then at the knife switches, you'll usually have one of the 250 to 600 amp fuses that we just talked about. At the end of each aisle of equipment is one of these. This is called a safety fuse, and it's the master fuse for the entire aisle, usually rated at 100 amps. Each frame in the aisle then has its own 20 amp fuse, sometimes more than one if the frame needs more power than that. Finally, each individual circuit is protected by a grasshopper fuse, usually rated at 1 1/3 amps. These are the ones that blow most frequently, and when that happens, it's usually my fault. These fuses are quite clever, and they have a bit of a story behind them. The reason we call them grasshopper fuses is because of these little tabs at the front and back of the fuse. When the fuse is in its normal state, the tabs are held in by the fuse wire. When the fuse blows, the fuse wire breaks and releases the tension holding the tabs in. The front tab pops out towards the user and serves as a visual indication that the fuse is blown. The rear tab contacts an alarm bar on the fuse panel, which diverts the 48 volt power to the office alarm circuit and rings the major alarm gong. Lamps throughout the exchange guide craftspeople to the source of the blown fuse so it can be quickly replaced and the equipment put back into service. All of these power systems were designed to be as reliable and as redundant as possible. On top of the things we talked about today, there were also gasoline or diesel-powered generators which can handle the entire building load for as long as they have fuel. These systems were updated and changed as new technology became available and was proven to work. In the last 40 years, solid-state power systems became the norm, and they required much less maintenance than the older power plants did. Although the newer systems are undoubtedly reliable and require much less human intervention than these older plants, I still like the older ones better. There's just something so cool about moving machinery and all of this super heavy-duty equipment. There's so much more we could talk about, and if I had time, we could do a deep dive on any single part of these old power plants. Leave a comment if you have any questions or a funny power story from your days working in the telco. At least 5 people have told me about the time they dropped a wrench behind the big power board and the wrench vanished from existence with a huge flash and a loud bang. If you like this video, give us a thumbs up and slam that subscribe button. Tell the important people in your life that you love them. Be kind. Get your pets spayed and neutered. See you next time.